Hi everyone, this is Srikanth as Assistant Professor of EEE Department. In this session, I am going to cover the common collector configuration of transistors. Here, the name itself says that the common collector, we are making the collector as common by taking input and output as base and emitter. Here in this terminal, in this configuration, the base terminal of the transistor serves as the input and emitter terminal will be serving as the output by taking collector as common. We are taking collector as common or ground point, and we are going to make the base as input and emitter as the output. And here the input is applied between the base and collector, while the output is taken from the emitter and collector. In the common collector configuration, the collector terminal is grounded. So the common collector configuration is also known as grounded collector configuration. In this common collector configuration, we are taking common terminal or ground terminal as the collector. That's why it is also called as ground collector configuration. And this is the way how the circuit is connected. Here the collector is made common between the base and emitter terminals. Here base and emitter terminal, this is the NPN transistor, and we need to make base junction should be forward bias and emitter junction should be reverse bias. That's why VBC and base junction is connected with a positive voltage, because base is a P junction, P layer. Base to collector junction is a PN junction. So here, when we have given the voltage, positive voltage, the base to collector junction will be forward bias. And whereas emitter is connected to the negative, so emitter is of N type and it is acting like a reverse bias junction. So emitter to collector junction is reverse bias and base to collector junction is forward bias. And here are the currents flowing. This is the base current flow and this is the collector current flow IC, and this is the emitter current flowing. So in this we are making the collector as the common, and we are giving the input to the base junction, base to collector junction, and we are taking the output from the emitter and collector junction. And here base to collector junction is forward bias and emitter to collector junction is reverse biased. In this common collector configuration is also referred as emitter follower or voltage follower, common collector amplifier, CC amplifier or CC configuration. This configuration is mostly used as a voltage buffer, because in this common collector configuration we can use for the voltage buffering of the circuit. That is the reason why this configuration is generally used for voltage buffering. And the input supply voltage between the base to collector is denoted by VBC, while the output voltage between emitter and collector is denoted by VEC. And the currents, as usual, how we have given the current in in the common emitter and common base configurations. In the same way, we are going to give the current and current directions based on the circuit connection, the base current, emitter current, and collector current. And here the common collector amplifier has high input impedance and low output impedance. Here this common collector configuration is having a very high input impedance and low output impedance. It has low voltage gain and high current gain. Here the power gain of the common collector amplifier is medium. To fully describe the behavior of transistor with common collector configuration, we need set of characteristics, that is input characteristics and output characteristics. As we have seen in the common base and common emitter configurations, we need to discuss the operation of these configurations based on the input and output characteristics. That is, input characteristics is nothing but whatever the input voltage which we are giving, that voltage versus the input current which we are going to get corresponding to that particular voltage. Here our input voltage in the common collector configuration is VBC, base to collector junction voltage. Here when we are varying the VBC value, how the IB is varying, that we need to see. Before giving the VBC value, we need to give some voltage across the emitter and collector junction, or we can also take it as 0 volts. And this input characteristics describe the relationship between input current or base current and the input voltage or base to collector voltage. And we need to draw a vertical line and horizontal line. Vertical line represents y-axis and horizontal line represents x-axis. The input current or base current is along the y-axis. Whatever the current is along the y-axis, and the input voltage or base voltage is taken on the x-axis. Here, in order to get the input characteristics, we need to keep VEC at some value. Let us consider that value as 3 volts. And now we are going to increase the VBC value from 0 volts to different voltage levels. For each level of input voltage VBC, the corresponding IB is noted. And then the curve is drawn between the input current and the input voltage at constant output voltage VEC. And this is the characteristics which we are going to get VEC at 3 volts. And now we can also go with the by increasing the VEC as 5 volts. Now the base to correct input characteristics will be shifted by some voltage. So it depends on the whatever the voltage which we are giving in the output terminals, as well as whatever the input voltage which we are changing, correspondingly how the input current is changing. Now we are changing the output voltage from 3 volts to 5 volts. Again we are going to draw the characteristics between, we are going to change the input voltage and we are going to note down the input current. Based on that, we are going to draw the another characteristics between the VBC and IB with VEC value as 5 volts. And we can also go with high values of fixed output voltage, and this process can be repeat for different values of emitter to collector voltage. Now we'll go with the output characteristics. Here the output voltage is emitter to collector voltage. Output current is emitter current. Here the output characteristics describe the relationship between the output current or emitter current, the output voltage or emitter to collector voltage, that is emitter VEC versus IE is the characteristics between the emitter to collector junction. These characteristics are also called as output characteristics because this emitter to collector voltage and emitter current are the output parameters. That is the reason why these are also called as output characteristics. First, the same way how we have taken the input, we need to take the vertical line and horizontal line. Vertical line represents the y-axis and horizontal line represents the x-axis. Now, the output current is taken along y-axis. We are going to take always the currents on the y-axis and the voltage on the x-axis. So the output current IE is taken along y-axis and the output voltage or emitter to collector voltage is taken along x-axis. And here in order to get the output characteristics, we need to keep some input current. That is, we need to give a small amount of base current or in or with zero, that is in microamperes we can keep, and the output voltage is increased from 0 and we are going to note down the emitter current. And then we have to draw the characteristics between the emitter current and emitter to collector current. For each level of output voltage VEC, the corresponding output current is noted. A curve is drawn between the output current IE and the output voltage VEC at constant input current IB. And here we are taking the IB value at 0 microamperes and IE value will be like this. We are going to get the output characteristics. It is a constant value. Whatever the voltage change VEC you can increase, there is no change in the emitter current. And this process can be repeated for higher values of base current. Here the base current is increased from 0 microamperes to 120 microamperes. Here first the base current is increased to 20 microamperes, and after increasing it to 20 microamperes, the when we increase the voltage VEC, and IE value will be maintained constant at 2 milliamperes. In the same way, when we go with 40 microamperes, the base current and the emitter current is reaching the 4 milliamperes and it is maintaining the constant. Like this, we are going to get the characteristics for 60 milliamperes, for 60 microamperes, we are getting the 6 milliamperes. whereas for 80 microamperes 8 milliamperes, for 100 microamperes 10 milliamperes, and for 120 microamperes we are getting 12 milliamperes. And this is the complete output characteristics of common collector configuration of bipolar junction transistor. Here, when during this period, when the IB value is 0, that is, there is no forward voltage which is applied. When the IB value is 0, no conduction will take place. No conduction will take place. So when there is no conduction takes place, that region is called the cutoff region. That region is called the cutoff region. And where all the currents are established, that region is called the active region. Here the base to base current is there and emitter current is there. So this region is called the active region. And during this region, that is during the 0 to -1, when the VEC value increases, it only takes some value and it will be maintained constant. And this region is called the saturation region. That means the transistor will go into saturation mode in this particular region. That's why this region is called saturation region. After this region, this will go into active region because it will be having the constant value throughout its operation. And here the next, the input current is increased from 0 to 20 microamperes, and we are going to keep at constant 20 microamperes. While increasing the input voltage, the output voltage is kept constant at 0 volts. After keeping the input current at 20 amperes, the output voltage is increased from 0 volts to different voltage levels. For different voltage levels, we need to note down the values of emitter current. A curve is then drawn between the output current versus output voltage at constant input current. This region is known as the active region of the transistor. And this process is repeated for fixed values of input current IB, 40 microamperes, 60 microamperes, 80 microamperes, and so on. In common collector configuration, the input current or base current is 0, then the output current or emitter current is also 0. Because when there is no base current, we know that bipolar junction transistor is a current control device. When we have given some input to the base, then only the transistor will be acting or it is going to work. Whereas when we don't give any base current, so there is no any emitter current because the transistor is not conducting. When the transistor is not conducting, no current will flow through the transistor, so the transistor will be in cutoff region. And if the base current is slightly increased, then the output current or emitter current is also increases. So the transistor falls into the active region. Transistor falls into the active region. If the base current is heavily increased, then the current flowing through transistor is also heavily increases. If the base current is heavily increases, the emitter current is also increases, as we have seen in the characteristics. Here is the characteristics where when the base current is increases, the same way similarly proportionally the emitter current is also increasing. And so once the emitter current increases, the transistor will falls into active region. If the base current is heavily increased, so the transistor falls into active region. If the base current is heavily increased, then the current flowing through the transistor also heavily increases. As a result, the transistor will falls into saturation region. Now we'll go with the transistor parameters. The transistor parameters are dynamic input resistance. Input resistance is nothing but what are the input parameters? What are the input parameters in common collector? Base to collector voltage versus base current. Here the dynamic impedance or dynamic input resistance, when we take the change in voltage divided by change in current corresponding to a particular output voltage. Here we are keeping the VEC value as constant. VEC value as constant. Ri is nothing but Ri is equals to delta VBC by delta IB. That is change in the base to collector voltage. Whatever the change we are going to make, correspondingly there will be change in the base current. That change we need to consider for calculating the input resistance. The dynamic input resistance is defined as the ratio of change in input voltage or base voltage to the corresponding change in input current or base current with the output voltage or emitter voltage kept constant. Here Ri is equals to delta VBC by delta IB, where VEC value is constant. Here if we take the graph is like this, we got the graph between the base current versus base to collector voltage. Now we need to, if we take any 2 points on this graph, the change in voltage, that is, this is VBC1 and VBC2. The change in voltage is nothing but VBC2 minus VBC1 divided by change in current. This is IB2 and this is IB1 divided by IB1 by IB1 minus IB2. So when we are taking these values, we are going to get the dynamic resistance, because we are taking the voltage and current values with change in the parameters we are considering. And next one is dynamic output resistance. The dynamic output resistance is nothing but it is the ratio between the output voltage by output current by keeping input parameter as constant. Here the input parameter we need to keep constant is the base current. Here the base current is kept constant and we are going to take the output voltage and output current into consideration while calculating the output resistance. Here the output voltage is of change in output voltage we need to consider, correspondingly change in input voltage, change in output current we need to consider. And here we are keeping IB is at some constant. The dynamic output resistance is defined as the ratio of change in output voltage or emitter voltage to the corresponding change in output current or emitter current with the input current kept constant. The output resistance of common collector amplifier is low. And here the current amplification factor. The current amplification factor is defined as the ratio of change in output current or emitter current to the change in base current or input current. It is expressed by gamma. The current amplification factor is equals to what is the output current by what is the input current, that is change in output current delta IE by change in input current delta IB. Corresponding changes we need to consider. Corresponding changes we need to consider while calculating the current amplification factor, where current amplification factor gamma is equals to delta IE by delta IB. Here the current gain of the common collector amplifier is high. Here is the voltage divider network. Already we have discussed. This collector, common collector configuration can be used as the voltage buffer. So here let us take the how the voltage is buffering with the voltage division equation. So here this is the input VCC collector, common collector voltage which we are giving VCC. This is the R1 and R2 if we consider. So the V output will be equals to VCC into corresponding resistance R2 by R1 plus R2. Therefore, what is the output voltage? Here is the VB. VB is equals to VCC into R2 by R1 plus R2. Here V output is equals to V input into RE, that is emitter resistance by RE dash plus RE, that is junction resistance plus resistance of the emitter. And here the current gain is equals to V output by V input, that is equals to IE into RE by IE into RE dash plus RE. Here RE value is much greater than RE dash, that is junction resistance. So RE dash plus RE can be considered as RE. So the two emitter currents IE will get cancelled. Thus AV is equals to V output by V input, which is equals to RE by RE, which is equals to 1. Now we got the current gain of common collector amplifier as 1. Now we'll go with one example, that is a common collector amplifier is constructed using an NPN bipolar transistor and a voltage divider biasing network. If R1 is equals to 5K6 ohms and where R2 is equals to 6K8 ohms and the supply voltage is 12 volts. Calculate the values of VB, VC and VE, the emitter current IE, the internal emitter resistance and the amplifier voltage gain AV when the load resistance of 4K7 ohms is used. Also draw the final circuit and corresponding characteristic curve with the load line. The base biasing voltage VB we need to calculate. For that, first we are calculating I, which is equals to VCC by R1 plus R2. VCC by R1 plus R2, that is 12 by 5600 plus 6800, which is equals to 968 microamperes, where VB is equals to I into R2, that is equals to 968 into 10 to the power of minus 6 into 6800, which is equals to 6.5 volts. Here the collector voltage we see, as there is no collector load resistance, the transistor's collector terminal is connected directly to the DC supply. Here the collector voltage is nothing but, when there is no load resistance, collector voltage is nothing but the VCC, that is same as the 12 volts. And the next parameter is emitter voltage, where emitter voltage is equals to VB minus VBE, that is equals to 6.5 minus 0.7 volts, that is equals to 5.8 volts. Thus VCE under off condition, VCC minus VE. Here VCE value is nothing but VCC minus emitter voltage we are going to consider. Here 12 minus 5.8, that is equals to 6.2 volts. And emitter current IE is equals to emitter voltage by emitter resistance. The common according to Ohm's law, where Ohm's law states that voltage across any conductive material is proportional to the current flowing through it, where current is equals to voltage across the conductive material divided by resistance of that particular material. So IE is equals to VE by RE, which is equals to 5.8 by 4700 ohms, which is equals to 1.23 milliamperes. And next, AC emitter resistance RE dash, where RE dash is equals to 25 millivolts by IE, that is equals to 25 millivolts by 1.23 milliamperes, that is equals to 20.3 ohms. And the voltage gain AV, which is equals to RE by RE dash plus RE, which is equals to 4700 by 20.3 plus 4700, which is equals to 0.996 or 99.6%. And for AC analysis of the circuit, the capacitors are shorted and VCC is shorted. Thus the equivalent circuit is given as shown with the biasing currents and voltages as given. Here, when we are going with the alternating current analysis, in this capacitors will be short circuited and VCC is also short circuited. So when we take the equivalent circuit will be like this, we are going to get the base to This is the base current V input, and this is the V output where we are going to take across the emitter. So here the load resistances R1, R2 which are connected to the input side, RE and RL is connected to the output side. Here RB base resistance is equals to, these two resistors are connected in parallel, where RB is equals to R1 is in parallel with R2, that is equals to R1 R2 by R1 plus R2, which is equals to, here RE is also effective resistance across the output terminals is also, these two RL and RE are connected in parallel. So when they are connected in parallel, the equivalent resistance will be equals to RE into RL by RE plus RL. Here the current gain beta is equals to IC by IB, and that is nothing but IC is equals to beta into IB. And here IE is equals to IC is equals to beta into IB. V input is equals to VB is equals to VB plus IE. V input is nothing but VB, base to emitter junction voltage, plus what is the emitter voltage. Here the input impedance of the common collector configuration, looking into the base as given as Z input is equals to R bias by Z base, where Z base is equals to VBC by VB by IB. But VB is equals to IE into RE plus RE dash, where IE is equals to IC plus IB, and IC is equals to beta into IB. And here Z base is equals to VB by IB, which is equals to IE into RE plus RE dash by IB, where IE is equals to IC plus IB, IE is equals to IC plus IB into RE plus RE dash whole divided by IB. From this, IE by IB is equals to beta into IB, beta into IB plus IB into RE plus RE dash by IB. Here IB will get cancelled. Here beta plus 1 into RE plus RE dash. This is the base impedance of the given circuit. Here as beta is generally much greater than 1, the expression of beta can be beta plus 1 can be reduced to only beta, because in order to get the simplified equation, we are taking Z base as beta into RE plus RE dash. Now the common collector amplifier input impedance Z impedance is equals to R bias is in parallel with Z base, where R bias is equals to R1 is in parallel with R2, where Z input is equals to RB into beta into RE plus RE dash. These two are in parallel. So in this session we have discussed the working of common collector amplifier, input output characteristics, and one solved example on the different parameters of the common collector circuit. Thank you. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.